So in this lecture, I will present an application of one of the dual variational problems I presented. So X will be a normed linear space, and Y will be a subspace of X. X star will be the dual of X. And remember that we represented by Y perp the set of bounded linear functional L in X star such that L of Y is equal to 0 for all Y in Y. And what we proved is that if you define L of Y as the supremum of Ly for all Y in Y, Y of norm less or equal than 1, then we have the following result. This supremum, it's equal to the infimum over all, well, of the norm of M minus L for all M in Y perp. And actually, we proved that this infimum is attained, so this infimum is actually a minimum. So here we have a dual variational problem in which a supremum is proven to be equal to a minimum. And I want to give you an example, a problem in which we will use this identity in order to solve it. So here is my problem. We want to send a rocket to a height equal to h. So xt will represent the position at time t of the rocket. So it's x double dot will represent the second derivative of xt. So the second derivative of xt, if you multiply that by the mass of the rocket, by Newton's law, it's equal to the force, which I will represent by Ft. So Ft, it's a force that you apply in the rocket, minus, well, the gravity force, which is m times g. So this is the equation satisfied by the position of the rocket. And at time 0, I will assume that the rocket starts from height equal to 0 and with a velocity. So x dot will represent the velocity or the time derivative of xt. Now this is equal to 0. So this is the equation which describes the evolution of this rocket, which at time 0 starts from 0. And we want to send it to some height h. So h will be fixed. And the problem is that there is a cost associated in putting a force Ft. So let's say that the cost t, it's given by the integral from 0 to t of the absolute value of this force. So say for the moment that f is continuous or bounded and measurable, so that this cost makes sense. And now what we want to do, it's, well, we want to minimize. So we want to find f. So we fix a time t, strictly positive. Now we want to send the rocket up to position h at time t. So we want it to reach position h at time t. And so we will apply a force, which will guarantee that at time capital T, the rocket attains this position. And we want to minimize the cost among all possibilities. So we want to find the solution of the following problem. So we want to minimize the cost, Ct, where Ct is given by this expression, according to, with the final condition that xt is equal to h. And this variational problem, so this infimum, it's carried over all f's, which provides this final condition. So let me be more precise about that. So let me explain this final condition. Well, we have this equation. Let's assume from now on that the mass is equal to 1. And, well, let's solve this equation to find xt in terms of f. So if I integrated once this equation in time, what I get is that x dot t, it's equal to the integral of the right-hand side. So this is integral from 0 to t of fs ds minus m, it's equal to 1. So what I get here is g times t. And there is no initial condition because I assumed that the initial velocity is equal to 0. So let's integrate it a second time and use the fact that you started from position 0 to get that xt. It's equal to this integral. So if you compute everything, what you get, you will integrate it by, so you'll change the order of the integrals to get that this is equal to t minus s times fs ds. And if you integrate the second term, this gives you minus gt squared. So now xt equal to h means that this expression at time capital T has to be equal to h. So what I want is that the integral from 0 to t, capital T, of t minus s fs ds, that this has to be equal to, this is h, minus in the other side gives you plus. This has to be equal to h plus g t squared divided by 2. So this is the equation x capital T equal to h. It's equivalent to this equation. So I will replace that condition by the condition that the integral from 0 to capital T of t minus s fs ds, then this is equal to h plus g t squared divided by 2. So I'm fixing capital T. Now I want to minimize this expression over all functions f, which are, say, bounded and measurable, such that the integral from 0 to t of t minus s fs, it's equal to h plus gt squared over 2. So this is my problem, the problem which I want to solve. And once I find this solution for a fixed t, then I will minimize that over all possible t's. So this is the variational problem I want to solve. I fix the height h, a positive time t, and I want to minimize this cost among all possible bounded measurable functions f, whose integral of this expression is given by h plus g t squared over 2. Now here is a remark. If you have, let's say, a measure mu on the interval 0t, which is absolutely continuous with respect to the Lebesgue measure and whose density is equal to fs. Then, well, what we know is that f has no sign, so that if you take the total variation of mu, so that this is equal to the integral from 0 to t of fs, the modulus of fs ds. So this is exactly what's appearing here. And on the other hand, if I represent by w of s the function, the continuous function which is equal to t minus s, so w, it's an element of the continuous functions defined on the interval 0t, well, I can rewrite this expression as, so the integral from 0 to t of t minus s fs ds. Well, this is the linear functional defined by mu applied to the function t. So if I represent by L of mu the element on the dual of the continuous functions applied to w, this is exactly, so remember, here, if I have a measure mu, which is of a sign measure and of finite variation, then this mu, it's an element of the dual of the continuous functions. And if I represent by L of mu the bounded linear functional defined on the continuous functions, L mu of u will be simply the integral from 0 to t of us mu ds. But now, if mu is the function which is absolutely continuous with respect to Lebesgue and whose density is given by f, L mu applied to y will be exactly given by the function w, which is the function t minus s, times the measure, but the measure is fs ds. So what appeared here is the norm of the measure mu, where mu it's fs ds, and what appeared here is the mu of omega, or L mu of omega. So if you wish to represent the application, the value at omega of the bounded linear functional generated, induced by the measure mu, this is mu of omega. And so if instead of considering this variational problem as a variational problem on bounded measurable functions f, I can consider it in a larger space, which is in the dual space of the continuous functions, so in the space of finite sign measure, and say that actually what I want to solve is the infimum of the norm of mu for all mu such that mu of omega it's equal to h plus g t squared divided by 2. So what I'm doing here, it's what we did before many times, is that to extend to a larger space this variational problem, because, well, maybe we don't expect the solution of this variational problem to be a bounded measurable function, but it might be something more general. It might be simply a measure on the finite sign measure, or positive, actually in this problem it will be a positive measure, which means a bounded linear functional defined on the continuous functions. So I enlarged the space of objects, the space of functionals in which I will solve the variational problem. So from now on I will consider this problem and we will solve this problem. So from now on I want to concentrate it on this variational problem. So I rewrote here the variational problem. I added this index t just to mean that we are working in interval 0t and that this is the norm of this measure taken as a dual, as an element of the dual space of the continuous functions defined on the interval 0t. Omega here, it's the function, the continuous function which takes the value t minus s at s. And this is the variational problem we want to solve. We want to minimize the norm of mu among all mu's belonging to the dual space of the continuous functions, for which mu of omega is equal to this expression. And my claim is that this infimum is equal, that we can compute explicitly this infimum. It's given by h plus h over t plus gt over 2, and that, well, there is one measure which attains this minimum, and this measure mu, it's the measure h divided by t plus gt divided by 2 times the Dirac measure at 0. So this is the Dirac measure at 0. So remember, if you have a function f on the space of continuous functions defined in interval 0 t, the integral of f with respect to this Dirac measure is just the value of f at 0. So this is, I want to prove this claim. And to prove this claim, let me first define Y as the linear space spanned by the function omega, W. So this is a linear space. And this is a subspace of X, which is the space of continuous functions defined on 0t. Now I want to define a bounded linear functional on X such that I will call it L0, such that L0 of W it's exactly given by this expression, h plus g t squared divided by 2. So we can use Han-Banach to prove the existence of such a bounded linear functional. You take Y, the space spanned by omega, so you use linearity to define L0 on this space Y, set L0 of W to be equal to this expression, and you extend it to Y by linearity. So at this point you have a bounded linear function defined on Y, and then you use Han-Banach to extend this bounded linear functional to L0, which is now an element of X prime. So here we are using Han-Banach. So there exists such a bounded linear functional, and now what we can write is that instead of writing this identity, I can just say that M of W is equal to L0 of W, or say that this difference is equal to 0. And now, well, let me rewrite this expression. Well, this is the same thing as minus mu of t, and I can rewrite this as L0 minus mu minus L0 of t. And so the variational problem which I want to solve is to find the infimum of L0 minus mu minus L0 t such that M minus L0 at W is equal to 0 with mu in X star. But if I call this expression mu hat, you see that what actually I'm trying to do is that I want to minimize mu hat minus L0 t with the condition that mu hat at W is equal to 0. And here mu hat belongs to X star. So to solve the first variational problem, it's enough to solve the second one. So to get mu hat and then observe that L0 minus mu is equal to mu hat, which means that mu is equal to L0 minus mu hat. So what we are going to do is, well, we will solve this problem, we'll find mu hat, and once we have mu hat, we can get mu through this identity and obtain the solution of the first problem. So I just rewrote the variational problem we want to solve. the condition. And recall that X is the space of continuous function. This is the dual, and Ws, it's T minus S. Now, requiring that mu hat of W is equal to 0 means that what we are actually asking is that mu of Y is equal to 0 for all Y in Y. And, well, we have seen that this variational problem, it's equivalent to the following variational problem. This is the supremum of L0 of Y for all Y in Y with norm bounded by 1. So this is the dual variational problem which I mentioned at the beginning of this lecture, and which we are going to use now in order to solve this variational problem. So this is very easy because Y, it's one-dimensional. So this variational problem, it's easy to solve. So this is the supremum. All elements of Y are in fact a scalar times W. So this is L0 of alpha omega, where I'm taking here alpha in R, such that the norm of alpha omega, it's bounded by 1. Omega, it's given here. So to require, this is the L infinity norm. So alpha omega, it's the norm of alpha times the norm of omega, but the norm of omega, you see that omega takes its maximum value at time 0, in which it's equal to t. So I need this to be bounded by 1. So this means that I want alpha to be less or equal than 1 over t. And now you remember that L0 of W was equal to H plus T square G divided by 2. So here, this is equal to the norm of alpha times the norm of L0 applied to W, but L0 applied to W is this quantity, which is positive. So this is H plus T G squared divided by 2. So what I want to maximize is the modulus of alpha times this quantity over all alpha which are bounded by 1 over t. And, well, it's clear that the maximum value is attained when the absolute value of alpha is equal to 1 over t, and therefore that this supremum, it's 1 over t times this expression. So this is exactly equal to h divided by t plus, t squared g, so t g divided by 2. Okay, so here it's t to the power 2 times g. And this was exactly my claim, that the infimum, the value of the infimum, was given by this quantity. So this is the first part of the proof. So we just proved that this variational problem, the infimum over all mu, it's given exactly by this expression. This is what we proved. Now I want to observe the following. Well, we have seen at the beginning of this lecture that actually this infimum, it's a minimum, because we transformed this problem into another variational problem, and that variational problem was exactly in the form of the beginning of this lecture. So if that one had a minimum, this one has a minimum. So there is one measure, mu, which attains this, this identity. So we know so let me call this measure mu, right? And we know since this variational formula, this infimum is given by this expression, we know that the norm of this measure, it's equal to h divided by t plus tg divided by 2. And we also know that mu of w is given by this expression. So we know that mu of w it's given by h plus t squared g divided by 2. But this is the norm of mu times t. So this is t times the norm of mu, right? Because, well, the norm of mu is given by this expression. And t, observe, t is the L infinity norm of w. So I can rewrite this as the norm of w times the norm of mu. And now I have an identity saying that mu of w is equal to the norm of w times the norm of mu t. And we proved a lemma which tells us that, well, in this case, you consider the continuous function w, and you see the number of points in which w attains its maximum. So here is the function. Modulus of w it's equal to the modulus of t minus s. And this function in the interval 0t attains its maximum at s equal to 0. And its maximum is t. Well, we have seen that if this identity holds, this means that mu can be written as a sum of Diracs. But in our case, since the maximum is attained at only 1 point, this means that mu is equal to beta times the Dirac measure at 0, because the maximum is attained at 0. And beta, it's given by the norm of mu. Well, but the norm of mu, we know exactly what it is. The norm of mu, it's h divided by t plus tg divided by 2. And therefore, this proves the second part of the claim, that the measure mu, which solves this variational problem, is actually a multiple of the Dirac measure. And which multiple? Well, this one. So we know exactly that mu is equal to h divided by t plus tg divided by 2 times the Dirac mass. So what did we prove? We proved that if we want to minimize this norm of mu among all bounded linear function, or among all finite sign measure mu, such that mu of w is equal to that, well, the minimum is given by this expression, and the measure, the finite sign measure which attains that infimum, it's a multiple of the Dirac measure. What does that mean? That means that if you fix a height h and a time t, and you want to send your rocket from 0 to the height h, and you want your rocket to be at height h at time t, and if you want to minimize the cost, where the cost is given by the norm of your measure, well, the best thing you can do is to input the all false at time 0. So actually you try to concentrate all the force on the rocket at time 0, and the force is measured in such a way that at time t, the rocket will be at height h at time capital T. But the message is that, well, the best strategy, if the cost is given by the norm of mu, is to concentrate all the force at time 0 or in the neighborhood of time 0. So this is what we just proved. Now, well, you want to try to minimize that over all possible times t. You just want your rocket to attain some height h. So now we can minimize over all possible times t. So now you want to, well, you solve that for a fixed time t, and you want to minimize that. So you want to minimize the cost, which is ht plus tg divided by 2 over all possible t's. So that's a very easy problem to solve. And what you get is that, well, the minimal is given by 2 times the square root of hg divided by 2. So this is the minimal cost, 2 times hg. So if you minimize that over all possible t's, you get that the minimal cost to send your rocket to height h is given by square root of 2 times the height times g. And the optimal time t is the one which minimizes this expression. So what you get is that t squared is equal to h2h divided by g. So the optimal time it's given by it's t. So let me call that t optimal. It's square root of 2hg. So this is the optimal time. With that time, this is the optimal cost. And by replacing t by this optimal time, you get the optimal measure. So the force you have to give to your rocket so that it will attain height h at a minimal cost will be given by, the force will be given by, as I said, the best strategy consists in concentrating the force in the neighborhood of time 0 and giving the total force as h divided by the optimal time plus t optimal g divided by 2. And this solves the problem. So you see that these dual variational problems are useful in concrete problems. This is a further example.